We've seen downsampling, we've seen upsampling, and we can see the reconstruction. So in the case that the aliasing components don't overlap, we can perfectly reconstruct the signal by using a suitable filter. Yeah? So we can make sure that they don't overlap by filtering the signal at the higher sampling rate before they can overlap, as we did in our high pass example. Yeah? If they already overlap at the lower sampling frequency, it will be too late to separate the different components and the signal will be already destroyed. Yeah? We can perfectly reconstruct the high pass signal in our example if we use ideal filters, yeah, using upsampling and the ideal high pass filtering. So in this way we have for analysis and synthesis the following picture. So here we had a high pass and we had downsampling. Here how the spectrum looks like after high pass, after downsampling, and then for synthesis we have upsampling, and then we have high pass filter, and we get this and this. So it's very interesting to observe that we violate the conventional Nyquist criterion because our high pass passes the high frequencies, yeah? But then the sampling mirrors those frequencies to the lower range such that we can apply the traditional Nyquist sampling theorem. So this method is known as the bandpass Nyquist. Yeah? The bandpass Nyquist is an important principle for filter banks and wavelets. Yeah? The bandpass Nyquist says that we can perfectly reconstruct a bandpass signal in a filter bank if we sample with twice the rate as the bandwidth of our bandpass signal, assuming we have ideal filters to avoid spectral overlap of the aliasing components. Yeah? In general, this is true for complex filters. For real valued filters, we need to observe that this simple assumption only works if we have bandpass filters which start at frequencies pi divided by capital N times k, an integer k. So otherwise we could have overlap to the alias components. Okay? So let's take a look at an example. So we have a real valued bandpass filter which starts its passband at epsilon and ends at epsilon plus pi divided by capital N. So since it's real values, the passband also appears at the same negative frequency. So we always need to consider the negative frequency. And after multiplication with the unit pulse train, we get out with one aliasing component out of N by shifting the negative passband by 2 pi divided by capital N to the positive frequency, which results in the range from pi divided by capital N minus epsilon to pi divided by capital N, 2 pi divided by capital N minus epsilon. So here we have an overlap from pi divided to capital N minus epsilon to pi divided capital N plus epsilon, and we could not perfectly reconstruct our signal. Yeah? So sampling of twice the bandwidth for real valued signals and filters only works if the bandwidth are aligned with pi divided by capital N times k. Yeah? And what could we do otherwise to avoid overlapping aliasing components? We can simply increase the sampling rate, for instance, to twice the usual sampling rate, so 4 times the bandwidth, to have a safety margin. Yeah. Another possibility would be to shift the bandpass signals in frequency such that they are now aligned with the mentioned grid. So this is an important thing to have in mind, that for real valued signals, yeah, these bandpass Nyquist theorem indicates that we must have bandpass filters which starts at frequency pi divided by capital N times k. So otherwise we could have overlap the ADAS components. And to solve this problem, or we can use a higher sampling rate, so 4 times, for example, the bandwidth, so having the safety margin, or we can also shift the bandpass signals frequency that in a way that they are aligned with this grid of pi divided by capital N times k. So observe that this restriction is not needed for complex signals or filter banks. This is also why complex filter banks are used for example, in acoustic echo cancellation, because there the sampling rate can be increased by a certain fraction, less than a factor of 2, to reduce aliasing artifacts and still have lower complexity. Summarizing, if our band borders are aligned with multiples of pi divided by capital N, then we can downsample by n. Otherwise, we are on the safe side by using n divided by 2 as downsampling rate for real valued signals. For complex signals, we can always downsample by n regardless of the exact placement of the bandpass filter. So here we're just comparing with the standard Nyquist case. We have a low pass signal which we downsample and reconstruct.